Welcome to homework.
So if we draw a free body diagram of the car, we see that mg is acting straight downwards. Then we have the normal force, which is perpendicular to the horizontal plane. We call it Fn. Then we have frictional force, which is working against the car. So if the car is moving from left to right, then frictional force is from right to left. We call it F of Fr. Now, if we apply Newton's second law on this system, we see that in x direction, we have f of x, which is negative f of fr. And now the reason we're taking negative is because we're choosing from left to right direction as our positive x, and from and upward direction as our positive y. So negative fr is equal to m times a. Now, since the car is not sliding, we can assume the friction or the maximum friction force using the static friction condition. So f of fr will be mu s, s as in static, times f of n. And what is f of n? We see that since there is no vertical motion, so f of n should be equal to mg. So this quantity right here is mu s times mg. Now once we know that, we can put that back in our fx equation, and we see that it's negative mu s mg is equal to m times a. And from here we see that a is equal to mu s times g, and then there's a negative sign. Now for the minimum stopping distance, we can use equation 2.12c and see that v squared minus vo squared is equal to twice a x minus xo, where vo is the initial velocity of the car, v is the final velocity, a is the acceleration, and x minus x naught is the displacement. So from here we see that displacement should be equal to x minus x naught, which is v squared minus vo squared divided by twice a. And as we mentioned that the final velocity is 0, and if we consider vo as small v, or our initial velocity v, we can replace this quantity as 0 minus v squared, and then we divide that by 2a. And also we saw that a is equal to negative mu s times g, so we can put that here, and we get negative v squared divided by negative mu s times g, which is equal to v squared over mu s times g. And then there's a 2 here. Right, so that's the displacement, and that's the algebraic solution for that. Now, with the given values, we see that v is equal to 95 kilometers per hour. We convert that to meters per second, and to do so, we multiply 1 meter per second by 3.6 kilometers per hour, which is 26.38 meters per second. Now, if we put that value over here and solve for x minus x naught, we see that x minus x naught is equal to 26.38 meter per second per square divided by twice of 0.65, which is mu s, times 9.8 meter per second squared. And that's equal to 55 meters. Now, in part C, we need to find out the distance if the gravity is changed, or if the car is on the moon. So we know that if the car is on the moon, the gravity is decreased by a factor of 6. So if we say gm as in gravity of the moon, that's going to be gravity of the earth divided by 6. So that means our displacement will be increased by a factor of 6. So previously our displacement x minus x naught on earth was 55 centimeters. So the same thing on moon will be 6 times 55 centimeters, which is 330 meters. Thank you.